Hello, everybody. Thank you for joining us today. Our research is on the use of Sentinel-2 and Landsat 8 satellite data for intermittently open-closed estuary monitoring. I'm Sarah Payne, and I'm joined today with Karina Alvarez. Other contributors for this project were Roger Lee and Molly Bruce. We completed this through the national program for NASA Develop at JPL, and we're really excited to be here today. And we'll jump right in. Next slide, please. So our objectives for this project, our primary aims were first and foremost to incorporate remote sensing to improve data collection of estuary and marine protected areas along the coast of California. Two, to design and build a tool in Google Earth Engine that assesses estuaries. And with this remote sensing tool, we hope to, three, identify if an estuary mouth is open, meaning it is connected to the ocean and subject to tidal influences, or closed, meaning it's separated from the ocean and not subject to those tidal influences. Next slide, please.
So for this project, we picked 6 study sites spread across the coast of California, and we took into consideration a couple different factors for picking these sites. Namely, we chose sites based on whether they were dynamic, so meaning that they opened and closed regularly. Based on size, we wanted somewhat of a distribution between large estuaries, for example, Drake's Estero, and smaller estuaries, for example, Ventura. And we also wanted to make sure that we were able to visualize these with satellite imagery at all. And so we didn't want anything that we wouldn't be able to visualize the estuary mouth dynamics for. Lastly, we picked estuaries based on their location. We wanted a somewhat even distribution up and down the coast. So we have sites in Northern, Central, and Southern California. Now for this presentation, we'll focus specifically on Navarro, as we were provided with Insitu water log data from our partners for this estuary, and we were able to use that Insitu data to compare with the outputs of this tool that we created. So once we had our study site selected, we were then able to determine and narrow down which satellites and sensors we were going to use to properly capture these dynamics. So for this study, we chose 2 satellite sensors. Specifically, we chose Landsat 8 operational land imager, as it provides a lot of flexibility in image selection and also has a bit more of a time series, as it started in 2013. And then we chose the Sentinel-2 Multispectral Instrument. Now this one has a finer spatial and temporal resolution, although it was launched a little bit later than Landsat 8. And so keeping in mind the length of time that the data from these satellite sensors is available for, we set the study period generally for 2018 to present. But for this presentation, we focus on January 2020 to August 2020 in the Navarro River Estuary, as this is the period when we had really thorough in situ data for. Next slide, please.
Hopping into our methods, we started by defining the study area of our 6 study sites. So we utilized the U.S. Fish and Wildlife's National Wetland Inventory as a baseline designation of estuaries, and the USGS 3D elevation project to include areas of potential inundation. So first, we clipped the USFS National Wetland Inventory to our 6 study sites. We then expanded that baseline area with the USGS 3 DEP DEMs. Those DEMs have a 1 meter resolution that we put at a threshold of 5 meters to include any areas that would be potentially inundated up to those 5 meters. And we did this in a repeatable manner as a way to standardize across sites. We also included a buffer that extended 2,000 meters into the ocean, and it was extended from a point at the estuary mouth 2,000 meters into the ocean. And this was to capture those dynamic ocean interactions that are essential to estuary ecosystems. And these shapefiles were then placed into Google Earth Engine for further processing. Next slide, please. We assessed the estuary mouth state conditions using Landsat 8 and Sentinel-2 imagery processed in Google Earth Engine, and Google Earth Engine was our platform of choice because we wanted to take advantage of its comprehensive database of free satellite imagery and its cloud computing technology. Google Earth Engine also allowed us to create an accessible and free tool that could help automate the process of estuary monitoring. And in the Google Earth Engine tool, we created a Normalized Difference Water Index, NDWI, which was thresholded to identify water from non-water pixels. And then to determine whether an estuary mouth was open or closed, we used pixel connectivity with a couple of Google Earth Engine functions. So as you can see on the image on the bottom right here, it would be considered one object if the water pixels were connected, and two objects if it was closed. And that was a simple way for us to determine the changes in estuary mouth state. Next slide, please.
All right, so now that we've run through all of our methods, we can start to chat about our results. So one of our big results early on was that Landsat 8 imagery was perhaps a bit too coarse for our purposes, especially for smaller estuaries. So this is an example of both the Sentinel-2 and Landsat 8 image from days in February, pretty close to each other. And what we see is that the berm in the Landsat 8 image on the right is represented by only 1 or 2 pixels at the thinnest points. And even a bit on the bottom part of the mouth, it can be a little bit difficult to determine what's happening there. And so we felt that Sentinel-2 would be a bit more promising, especially because we do have estuaries of differing sizes, including some ones on the smaller end that would benefit from a higher spatial resolution. So before we get into really comparing the in situ data with the output of the tool that we created, we want to get familiar with the in situ data that we had. And so what we have here is a time series of water level from water loggers over time. And we see that it's quite variable, but overall there are 3 pretty substantial and visible dips in water level. And those can represent when a breach event occurs. So when the estuary mouth opens, releases a lot of water and results in much lower water level. These dates are important because we can then identify these dates as breach events and compare that to the dates that we're able to see with the satellite imagery and assess if we're actually capturing what's happening on the ground. Next slide, please.
Here we see a figure with the results of running the mouth state analysis on the Navarro study site. We have dates from February to June of 2020, and every dot is an image that made it through our cloud filter. Blue is a closed estuary mouth, yellow open, and green is in situ data from the previous slide indicating a breach event. General trends is that our tool was able to capture changes in mouth state, which was really exciting, and sometimes it captured it directly after a breach occurred. And with this chart set up, we want to walk through a couple of images step by step to really analyze how well the tool ran. Next slide, please. On this slide, we're highlighting 2 dates, February 7th and February 12th. And as seen by the chart on the top right with the blue dots, our Google Earth Engine tool deemed both of these images as having a closed estuary mouth. While on the other hand, our in situ water level data suggests that a breach occurred between these 2 images on February 11th that wasn't properly captured in our tool. And with that conflicting information, we take a look at the NDWI images, which are a produced output from our C tool, and see if we can identify a breach. On the left, it looks like the estuary mouth is closed, while on the right, it looks like it's open through a small channel in the mouth there. Another sign that it was truly open on that right image is the level of inundation. As you can see with the red circle here, the water level decreased on the image on the right when the mouth was open. And while the second image here, we were not able to properly identify the breach, having a high temporal resolution in our imagery really comes in handy in our analysis, as we can see on our next slide. So here we have the same setup with different dates. We're moving along the chart to February 17th and February 22nd. Both images were determined by the Google Earth Engine tool as open, and in situ data suggests a breach recently occurred. And with the tool and the imagery and the in situ data in alignment, it was really exciting to see our tool properly capture the estuary mouth state here. Even with the stream being fairly small connecting to the ocean, we were still able to run this analysis properly. Next slide, please. And to bring it full circle, here we have the estuary mouth as closed again. Both Google Earth Engine and the NDWI show a clear closed estuary mouth. And it's interesting to note the levels of inundation are starting to build back up again, just like that first image in February 7th, 2020. Overall, these results from our mouth state analysis show how over the span of a few days, our Google Earth Engine tool was able to capture some pretty dynamic mouth opening and closing processes.
So to wrap up our results, we want to discuss some errors, uncertainties, and potential solutions for those uncertainties. One of the main challenges that we had was cloud cover. So what we have here on the left is a graph of the percent cloud cover in an image over time. And then we have on the right 2 examples of images that have clouds and pose a little bit of a challenge. So on the top, we see that we have clouds present in this image, although it's not detected as having a high percent cover of clouds. But because they're not really around the estuary mouth, we're able to visualize the dynamic there, see that it's closed, and still likely get a correct reading. If we look at the bottom image now, we see that although there's a really low percent cloud cover detected, or according to the metadata, most of the estuary is actually covered in cloud and would be inaccurately assessed by NDWI as land or as not water. And so our tool wouldn't be able to discern what is the actual mouth state here. And so we're hoping to figure out a way to have more accurate assessments of cloud cover so that it doesn't impede our analysis with the tool. Next slide, please. So to conclude and chat a little bit about our future work, we see that this tool provides near real-time snapshots of estuary mouth state. Because the platform is really frequently updated, you're able to access images really soon, just a couple days after they're collected. And we see that Sentinel-2 specifically works really well for deriving NDWI and for coming up with this land-water binary, and then determining the estuary mouth state from that. As far as future work, we're hoping to further validate and verify using Insitu data from our partners, of course, improve our cloud mask, create a graphical user interface so that individuals with and without coding experience can use this tool, and then incorporate some other elements, perhaps inundation extent like Sarah mentioned briefly before, and other sites across the coast, and even maybe further beyond that. And before we wrap up, we just want to shout out and give some acknowledgement to the other people that were really involved in this project. Next slide, please. Specifically our science advisors at JPL, including Ben Holt, Christine Lee, Bruce Chapman, and then our fellow Erica Carsland, as well as all of our partners who were really involved in giving us really meaningful and helpful insight in developing the project, as well as collected the Insitu data that we used. Now with that, we will wrap up. Thank you for listening, and we're looking forward to chatting with all of you.